Hello everybody. In this video we're going to start to look at the energy involved when you make a solution. When you mix two things together, sometimes energy is absorbed, sometimes it's released, sometimes it feels cold, sometimes it feels hot. We're going to look at the calculations that determines that and why some solutions would be endothermic mixing and some would be exothermic. So the definition of the heat of solution is the amount of heat energy either absorbed or released when a specific amount of solute dissolves into the solvent. And you can see here just some examples where sometimes it's endothermic with a positive value and sometimes it's exothermic with a negative value. You'll notice they will often have units like kilojoules per mole. So it will be important to look at the quantities involved when you're doing all your calculations. Sometimes when you mix things like sodium hydroxide, when you put that in water, the container will feel hot. It's releasing heat. It is exothermic. However, sometimes things like ammonium nitrate will result in the container feeling cold. Have you ever felt one of those instant ice packs? Typically there's a little bubble of water or something inside and you crack it open. When you bend the container, when you pop that internal little bubble, mixes with the chemicals and the ice pack gets cold. It's absorbing the energy from the surroundings. So it's taking energy out of your arm or your knee or wherever it is you're putting the ice pack. So let's think about why this might be. When you're going to make a solution, people don't often think about the physical steps that have to occur. You just dump it in and stir, right? So let's think about what's happening on a particle level here. So if we want to make a solution, you have to take all of the solute particles and spread them apart. So the energy involved in the first step of pulling your solute particles away from each other is endothermic. It takes energy to spread those away. Step 2, you got to spread out some of the solvent molecules also. You need space to mix in those solute particles. So that's endothermic. And then you're going to start forming new attractions between the solute and the solvent. And when we're making these new attractions, there's a release of energy. So that mixing part is exothermic. Remember, it takes energy to break bonds, to break attractions, and energy is released when new ones are formed. Positive values up here, negative value down here. I have little pictures that try to show these 3 steps, so let's look at those. In a second, let's look at it in an equation first. To get your overall delta H, you would add up all your pieces. You'd have a positive value, and a negative value. So you can see here, step 1, we have this really close solute, and we're trying to pull them apart further away from each other. Then in step 2, right now, the solvent is so close together, there would be no space to put those solute particles in. They need room. We got to spread these apart. And then when you combine them, now there's space for all our solute to mix in. and these start to attract each other, forming those new attractions, and that part is exothermic. If it was more energetically favorable to have the solute interact with the solute and the solvent interact with the solvent, then they wouldn't mix, would they? But because this is a more favorable set of attractions, it released that energy. Now it's exothermic. And now it actually happens. You'll often see pictures like this. Does this remind you of lattice energy? It reminds me of lattice energy a lot. You gotta pull things apart and then you combine them together. Some of it's endo, some of it's exo. So what decides whether or not the overall process is endo or exothermic is down here. Do you see this red arrow down here? What's the net process? If more energy is released when they mix than it took to separate everything apart, then it would be exothermic. Compare that to if it takes more energy to separate everything than it does to mix them together, then it's endothermic. You have a net gain, right? You had to put in more energy than you got back. It's endothermic. More was absorbed than was released. So you can think of it in terms of when we're endothermic, your solute and solvent attractions are not as good as the solute and then the solvent. And if you think all the way back to our thermodynamics chapter, remember energy is only one part of this. This would not be a favorable condition from an energy standpoint. So the only way that solution will actually form, the mixture will actually happen, is if you get such an increase in entropy that outweighs how bad this energy situation is. So you have to always think about not just the energy, but also the entropy, which is a throwback to our very, very, very early chapter. So you can see here, they just tried to tabulate the different combos that you could get. Now, we often hear this phrase, like dissolves like, or like mixes with like. And it's just a way to remember that nonpolar things like nonpolar things. These are some common examples that you might see. We have some organic solvents over here. Things like fat and waxes, oil, right? And then polar things, like polar things. And here are some common examples that you might see. It is not that they expect you to know what the formula or structure of toluene looks like. They don't expect you to know what the structure for a steroid looks like. But I would be familiar with some of these examples. They will typically give you charts of data. Or you may not know what the solute is, but when they tell you it dissolves in water, you know that means it's polar. So you can kind of use that logic to figure out what the polarity might be. And one of the things that you should start being able to do is go a bit further than like dissolves like. That's a great way to remember it, but I want you to start talking about the fact that the reason these happen, let's go backwards a few slides here, has to do with this overall process. Spreading things out and then mixing them together. Do we have a net exothermic, net endothermic? What was the scenario with the attractions? Was the mixture attractions better or was it worse? Right? This, and thinking about, the interactions between solute and solvent explains why we see like dissolves like. It is more favorable for water to mix with sugar than it would be for fat to mix with water. So do you remember back in our thermodynamics chapter, we had charts that would help you make predictions about whether something would happen, where you were looking at whether it was endo or exothermic, increase or decrease in entropy, high temperature, low temperature, and you would use those kind of big categories to decide if it was a favorable combo or an unfavorable combo for delta G. We do that a lot with predicting solution formation as well. So we have a very similar feel of a chart. So you can see here that we have our solute and our solvent. So in our first example, they're both polar. Because they're polar, there's a large amount of energy required to separate the solute from itself and from the solvent from itself. But you also tend to get a large exothermic release when they mix. Depending on the exact numbers here, usually a solution will form. Usually this will result in a negative value. If you have a nonpolar solute, it won't take very much energy to pull apart. It'll take a lot to pull the solvent apart because it's polar, but you're not going to get much interaction there. That's not really going to release much energy. So you typically end up with a large positive value, which means it's not favorable typically. Unless something about that entropy is going to way outdo it, your solution won't form. So the best combo, remember we would always think about which was the best combo for delta G. It was exothermic and high change in entropy, high increase in entropy. We have a similar thing here. The factors that favor the formation would be that the overall solution is exothermic and that we have a large increase in entropy. If your delta H of solution is positive, you got to look at the entropy and then maybe it'll still occur. So the solutions chapter can be a sneaky way to bring back your Gibbs free energy calculations, right? Remember, we always talked about how thermodynamics and equilibrium always get sucked back into things. Well, it's going to probably happen here too. All right, everybody, that is it for this lesson. I hope that was helpful. Bye.